Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering. And this is Module 1, an introduction to probability and to set notation. So basically, the purpose of probability theory is to help us deal with uncertainty. And most of you, if you've got an engineering background in your undergraduate careers, will have taken at least one class on probability and statistics. But for the most part, your education will have concentrated on deterministic phenomenon. And when we say something is deterministic, it means that we can completely predict how it's going to behave. So for example, if we're dealing with kind of a classic sinusoid, that looks something like this. As long as we've got the equation for the sinusoid, we know its amplitude and its frequency and maybe its phase. We know exactly what that waveform is going to do at all points in time, so there's no uncertainty at all. However, there are lots of cases in kind of advanced undergraduate topics, and certainly in graduate topics and in research topics, and in industry, where we deal with phenomenon that cannot be completely predicted, and we call, when we're dealing with something like this, we call it random. And probability theory cannot help us predict exactly what's going to happen when we're dealing with a random event. However, what it does is provide us with mathematical tools that will allow us to indicate how likely a random event is going to occur. And so when we deal with probability, we basically assign random events a number, and this number indicates how likely or unlikely it is to occur. And this is really sort of fundamental to the idea of probability theory. And most people, I find, even even if they're not from engineering, have some intuition about this already. For example, if we're listening to the weather forecast, everybody knows, particularly in Calgary, that weather is essentially a random phenomenon. We can't guarantee typically that it's going to rain on a particular day or it's not going to rain on a particular day. However, we do listen to weather reports, and a weather report will say something like, oh, there's an 80% chance that it's going to rain today. And when we hear something like that, we know that we better pack an umbrella. By the same token, if the weather forecast says there's only a 10% chance that it's going to rain, then probably we won't bother and we'll leave the umbrella at home. And so this number, this percentage, is a probability value that we assign to a random event, in this case rainfall, that will tell us whether or not something is, or that will basically give us an intuition or a feeling how likely something is to occur. And so what we're going to start off with in this class is talking about a couple of ways that we can come up with these probability numbers if we're dealing with something random. So the first method we can talk about for finding probability values is something that's known as the classic definition of probability. And it can be used whenever we're dealing with a random experiment or a random phenomenon when all possible random outcomes are equally likely. So an example, a non-engineering example of this would be rolling a six-sided dice. You roll the dice and all numbers are equally likely to occur. A coin toss is another example. And so basically, to use this definition, we define some event A that we're interested in, and the probability of A occurring is the number of outcomes that are favorable to A divided by the total number of outcomes. And so if we use the six-sided dice example, the probability of rolling a 4 is equal to 1 over 6. There's only one outcome that's favorable to the event 4. That's actually having a 4 come up on the dice. And there are 6 possible outcomes. However, we can also say the probability of rolling an even number is equal to 3 over 6. right? Because there's 3 numbers on a 6-sided dice that are even and 6 total possibilities. So the probability here is just equal to 1/2. And so that's an example of an event that has that corresponds to more than one outcome from our experiment. And just as a little bit of notation here, you'll see already that when I'm talking about the probability of a random event, I use the capital P here, and then the random event, whatever we're talking about, rolling a 4 or having an even number, is inside round brackets. A second definition is the relative frequency definition of probability, and this one is maybe a little bit more experimentally based. And let's say again we're dealing with some sort of random experiment, I guess, or some sort of experiment or physical process with random outcomes, and we define a random event A that we're interested in, and we want to determine the probability that A occurs. We can do this experimentally by conducting n random experiments and basically counting the number of times that A occurs. And the number of times A occurs is equal to NA. And so the probability of A occurring is equal to NA divided by the total number of experiments that we do. And the idea is that as we perform a large number of experiments, we get a very stable and reliable estimate of the probability that A occurs. The question of how many results do we need to capture, that's basically a statistics question. So we're going to talk very little about statistics in this class. We're going to assume that probability values and the data has already been processed and put into sort of a probability framework. But if you're interested in sort of coming up with like a confidence interval for how many experiments you need to do, that is something that you should open a statistics book to find that out. A good kind of rule of thumb, I guess, would be keep performing the experiment until your estimate of the probability of A stabilizes. If you find that it's jumping around still a fair bit, you need to conduct more experiments. And so as an example here, let's say we were tossing a coin and we wanted to figure out the probability of a head. We would, let's say, toss the coin an infinite number of times, and we would count heads exactly half the time. That doesn't mean that every second outcome is a head. We may get a string of tails in a row, but if we do the experiment long enough, the number of heads and tails will even out. And that's why the definition requires that we have a large number of experiments, or we conduct a large number of experiments. So now, in theory, any probability value can be determined using a relative frequency style experiment, right? You set up your experiment, or you create your engineering system. Maybe there's random noise in that system or something like that. And you just run the system, you perform the experiment a huge number of times, and you count all the possible outcomes, and you come up with your probability values. That certainly is possible, but it can be time-consuming and expensive, right? Particularly if you're working in the lab and you want to graduate in a reasonable amount of time, you don't want to be conducting an infinite number of experiments. And also, when you're working in industry, you don't want to be using company resources to perform tests over and over again. And so a lot of the value of probability theory, and what we're going to be learning in this class, is how to take just a few probability values for a few outcomes from a random process or a random experiment, and manipulate those values to come up with probability values for other events that maybe we didn't do an experiment for. And this is really, really important, and it's really the value of mathematics in general, right? What we're trying to do is we're trying to replace a physical experiment with a cheaper, quicker thought experiment that we can do with mathematics. And so we're going to find that one of the very useful tools that we have for manipulating probability events and coming up with probability values for experiments that maybe we haven't done is set notation. So we use set notation quite a lot. And what I'm going to do sort of over the next few slides is just introduce a lot of sort of ideas and concepts in set theory, a lot of definitions, and gradually we're going to sort of transition into using these ideas to determine probability values. So fundamentally, a set is just a collection of objects called elements. And the example I have here on the slide is the set A contains 6 numbers, 1, 2, 3, 4, 5, 6. Our notation is we use these curly brackets or braces to sort of surround a set. In this particular case, and in a lot of our examples, the contents of our set contains just numbers, but that does not necessarily have to be the case. You can create a set that contains colors, red, orange, and blue, for example, in which case you would have the words red, orange, and blue, and you would surround it by braces. So the number of elements in a set is called its cardinality, and it's denoted using this magnitude notation. And so the cardinality of our example set would be 6, right? Because we've got 6 elements. These symbols indicate whether or not something is or is not an element of a set. So for example, we would say 2 is an element of A, but red is not an element of A. The empty or null set contains no elements at all and is denoted by this symbol. And a very important concept, particularly for probability, is the notion of a universal set, or the space of an experiment. And the universal set contains all possible elements that are relevant to a particular context, which is kind of a vague definition, but more specifically for us, when we're dealing with a random experiment, the universal set contains all possible outcomes of our random experiment. So if we're rolling a 6-sided dice, our universal set would contain all 6 numbers, which are the only outcomes possible from our random experiment. The universal set is typically denoted using the letter S, which is, stands for space. And, in a lot of the examples that we're going to be doing in this class, it's kind of trivial to define the universal set. But when you're working in your own research, it may not be trivial. So there may be an experiment where, you're expecting certain outcomes. Maybe you're monitoring a control system, and you're expecting only positive values from a certain sensor, and you conduct your experiment, and you find that there's some problems. Your signal is cutting out, and then maybe your signal perhaps goes negative some of the time as well. So you do have to be careful defining your universal set for a lot of practical situations. The concept of a subset is also important. So a subset of A is a set whose elements are all elements in A, or they all come from A, or they're all contained in A. So for example, if we have a set B that contains 1, 3, and 5, all these numbers are inside A, or contained in A, so we would say that B is a subset of A. But C contains 3, 5, and 10 would not be a subset. Notice that all the elements have to come from A. So 3 and 5 obviously come from A, but because 10 does not, we would not consider C to be a subset of A. This is our subset notation. So this indicates that B is a subset of A. Sometimes we say that B belongs to A, although I won't use that terminology very much in the course. And it is valid to say that A is a subset of itself. For any set, we say that the null set is a subset of any set at all. So at the very least, a set has to contain nothing, I guess, is the intuition there. We've already said that A can be a subset of itself, and all sets have to be a subset of the universal set, because the universal set needs to contain all possible outcomes relevant to our particular experiment. There is also the concept of a proper subset. So this is a slightly different notation. A proper subset is a subset that cannot be equal to the superset. So you could never write something like this you always have to sort of put that line under there, which, you know, and the line kind of looks like it's a little bit of an equals sign, so that helps you remember. The notation can be used to illustrate transitivity. So if C is a subset of B and B is a subset of A, then we can say that C is also a subset of A. And also we can use it for equality. So if A is equal to B, then A has to be a subset of B, and B also has to be a subset of A. Another useful tool when you're dealing with sets is what's known as a Venn diagram. And a Venn diagram is basically just a diagram showing blobs or shapes, and whether or not these shapes kind of, and each shape basically represents a set, and whether or not they intersect with each other or they're inside each other allows us to say something about the sets that they represent. So specifically for the idea of subsets, if C is a subset of B, then on a Venn diagram, if we have a shape that represents B, then the shape C has to be completely inside B, right? So it can contain only elements from B, but it can't be equal to B because this is a proper subset that we're referring to here. And so it can't be exactly the same shape as B. It has to be a little bit smaller than B, and it always has to be inside B. If B is a proper subset of A, then it has to be contained inside the larger shape A. And here, of course, we can see the transitivity idea quite clearly. If C has to be contained completely inside B and B has to be contained completely inside A, then obviously C has to be completely inside A as well. So a particularly useful aspect of set theory when we're applying it to probability problems is the operations that you can perform on sets. And we're going to be doing a lot of these operations to kind of manipulate sets that we associate with the random outcomes of experiments. And these manipulations are going to allow us to calculate probability values based on other probability values. And the first operation that we're going to talk about is the sum or the union of two sets. And the definition, the basic definition of a union of two sets is a third set that contains all the elements that are in both of the sets that we're taking the union of. And there's sort of two notations that we can use to indicate union. The first one is this cup, or this, which is easy to remember because it looks like a U. So the union of A and B is A cup B. You can also use the plus operator to indicate union as well, although I won't be using the plus operation that much in this course, just because it can be kind of confused with addition. And just as an example to show how union works, if A contains the sets 1, 3, and 5, and B contains, or sorry, if A is a set that contains the elements 1, 3, and 5, and B contains 3 and 6, then the union of those two sets contains all the elements from both 1, 3, 5, and 6. One thing you'll note, though, is that we don't double count elements, right? 3 is an element in common to both A and B, but it does not appear twice in the union. Now, one really important thing that we're going to be learning in this class is how to translate a verbal description of a problem into sort of mathematical probability notation that will allow us to perform some calculations. And I think that this is particularly important for engineers because we are not mathematicians. The purpose of an engineer is to apply science and to apply mathematics to the real world. And so we need to be able to take a plain language verbal description of a problem and translate that problem into math. And we're going to be getting practice doing this on the assignments, and you're going to be doing these kinds of problems on the exams as well. And one of the things that we're going to be looking for as we sort of translate these verbal problems into probability terms are sort of keywords. So is there something in the language of a problem description that allows us to associate certain operations to it? And one of the words associated with the sum or the union operator is the word or. So if you see the word or happen in a problem, let's say, what's the probability of rolling a even number on a 6-sided dice or rolling a 4, as soon as you hear the word or, you should think, aha, that's a union operator. And we can apply the union to that problem. One thing I should point out, though, is that or is, in set theory, is inclusive, right? So if we have elements, or if we're taking the union of the set A and the union of the set B, we would say we're calculating A or B, which means all the elements in common. And that's a little bit different than sort of the normal plain language usage of the word or. We often use the word or to, I guess, describe two events that you have to choose one, but you can't have both. So your mother might say, you can have cake or cookies, and what she's meaning is that you can have cake or cookies, but you can't have both. But in probability terms or in set theory terms, you can have both as well, I guess. So you can have cake and cookies. Just a few more details about the union operator. It doesn't matter what order you do it in. So A union B is the same as B union A. If you've got a string of 3 union operators, you can take the union of A and B first, and then the result of that union, you can then calculate the union with C, or you can determine the union of B and C, and then take the union with A. Doesn't matter which order you do it in. Also, if we think about a situation where we have B as a subset of A, right? So if we draw our Venn diagram, if this is A, then this would be B. The union of A and B is just equal to A. And we can see that because since B is completely contained within A, all the elements of that A and B have in common are completely contained within A as well. We can also say that the union of A with itself is just equal to A. The union of A with the null set is equal to A because the null set is a subset of any set. And by similar reasoning, the union of A with the superset or the universal set is equal to the universal set because all sets have to be contained within the universal set. The next operation is the product or intersection operation, and the product of two sets, or their intersection, consists of only those elements that they have in common. And we can denote an intersection using an upside down cup, or just by putting the two sets side by side, which is similar to an algebraic multiplication. And I will use both notations in this class fairly commonly. And so just to illustrate how intersection works, if A contains the numbers 1, 3, and 5, B contains 3 and 6, then their intersection is the element 3, because that's the element that both sets have in common. If we are translating a verbal problem description into probability terms, and we see the word and generally means intersection. So if we say, what's the probability that we have a failure and the unit has overheated, that generally means that we're taking an intersection operation when we're translating those problems into probability terms. And again, we'll have lots of practice with this, and we'll see how this works later on in the class. Intersection, like the union operator, doesn't matter what order you do it in. If you've got the intersection of 3 sets, you can take the intersection of the first two first, or the second and third first. Also, similar to multiplication and addition, if you're taking the union of B and C and then taking the intersection of that result with A, you can take the intersection of A and B and A and C first, and then take the union of those two results. Looking again at a subset situation where we have set A as a subset of a larger set B, then the intersection of A and B is just equal to A. And that's because the only elements that the two sets have in common are in fact all the elements contained in A. This means that the intersection of A with itself is equal to A. The intersection of A with the null set is equal to the null set, because the null set is a subset of any other set. So if we wanted to talk about this in terms of plain language, the intersection of something with nothing is nothing. And the intersection of any set A with the universal set has got to be equal to A, because A is a subset. Any set A has got to be a subset of the universal set. And just to conclude with a Venn diagram kind of example, here we have two sets A and B. They have some elements in common and some elements are not in common. And we draw that on a Venn diagram by showing the two shapes overlapping partially but not completely. And so the intersection of A and B will be this region that they have in common. And the union of A and B will be all of B, all of the region they have in common, and all of A as well. So the notion of mutually exclusive sets are basically sets that have nothing in common, right? So two sets A and B are mutually exclusive. If they have no elements in common, very easy to think of many examples of this. We would say then that their intersection is equal to the null set, or in other words, they have nothing in common. And if we were to draw them on a Venn diagram, A and B would look like this. They would not intersect at all. Complement is another useful and important idea. The complement of A basically defines a second set that contains all of the elements in the universal set that are not in A. So for example, if we've got our six-sided dice experiment and A is equal to 1, 3, and 5, then the complement of A is equal to 2 and 6. And so it's important, I guess, to remember that you can't determine the complement of a set without also having knowledge of the universal set. And if we were to draw a Venn diagram of this, I usually draw the universal set as a square, just to make it a little bit different. And if we have a set A that, of course, has to be contained inside the universal set, then the complement of that set is basically the entire region in the universal set that is outside of A. So it follows from this definition that the union of A and its complement has to be equal to the universal set. The intersection of A and its complement has to be equal to the null set, because a set and its complement can't have any elements in common. We also say that the complement of the universal set is equal to the null set, and the complement of the null set is equal to the universal set. So if you don't have everything, you have nothing, and if you don't have nothing, then you have everything, I guess, basically is what those are trying to say. Moving on to the idea of partition. The partition of a set, in this case, I'm using the universal set, but it doesn't have to be the universal set necessarily. The partition of a set is a series of mutually exclusive subsets that completely define S. And when we say completely define, it means that the union of all of those sets equals the set that we're taking the partition of. And so for the six-sided dice example, we have A1 equal to 1, 2, and 5, A2 equal to 3, and A3 equal to 4 and 6. So if we take the union of these three sets, we have the numbers 1 to 6, which is equal to the universal set of our experiment. But as I said, it's not completely necessary for us to be taking the partition of the universal set, although it is something that we will do actually a fair bit, and it'll be particularly useful later on for us when we're working on probability problems. Another way that you can visualize or think of partition is using a Venn diagram where we have our universal set S, and you can think of a partition kind of as, the way you might chop up a cake, right? So you've got a square cake and you want to chop the the cake into pieces, so the pieces can't overlap. And then you define your sets A1, A2, A3, and in this case we would have A4. And if you take the union of all four of these sets, then you're left with the universal set. The difference between two sets is denoted A minus B, right? Like subtraction, or the mathematical difference. And it consists of all the elements in A that are not in B. So in other words, A minus B is equal to the intersection of A and everything that isn't in B. And so if we were to draw a Venn diagram, let's say we have A that intersects a little bit with B. And so the complement of B is all the elements that are outside of B. So it cannot include the intersection, the intersecting region. And so the difference then has to be equal to the portion of A that is not equal to B. So this is what the difference would be. And so using a numerical example, if A contains 1, 3, and 4, and the set B contains 3 and 5, then A minus B is 1 and 4. So any elements in common have to be removed. So there's kind of an interesting contradiction here to test your knowledge, I guess, or to test how closely you've been following all this set theory stuff. So we know that the null set is a subset of any other set A, and that A always has to be a subset of the universal set. However, we've also seen that the complement of the null set is equal to the universal set, which suggests that the null set and the universal set are mutually exclusive, right? Because one is the complement of the other. So if that's possible, if the null set and the universal set are mutually exclusive, then how is it also possible for the null set to be a subset of the universal set, which is what's suggested by what we have up here? So if you want to, you can just pause the video for a second and think about it, because I'm going to give you the answer on the next slide. It basically has to do with the fact that we've used the null set as part of our definition of mutual exclusivity. So if A and B are mutually exclusive, then their intersection has to be equal to the null set. And so that means that if the null set and the universal set are mutually exclusive, then their intersection has to be equal to the null set, just because of the way that we've defined it, right? We know, though, that if, by definition, if the intersection of A and B is equal to A, then A must be a subset of B, which means that the null set must be a subset of the universal set as well, basically because of this definition here. Okay, so that's all the basic set theory notation I really wanted to review with you guys. The next step is basically to move on to actual probability theory and to use these set concepts as tools. But to do that, just one last slide, basically with some terminology or definitions. Often when we're talking about the universal set for a random experiment, we call it the sample space. I'll use both terms kind of interchangeably from now on. The sample space is the universal set that contains all possible outcomes for an experiment. So for our six-sided dice, the sample space S would be the numbers 1 through 6. When we talk about an outcome, we're talking about the elements in an experimental sample space. So all of the possible outcomes that can occur from a random experiment. And an event, a random event, are basically subsets of the elements in the sample space. And you might say, well, isn't everything in the universal set an event? It is. when we talk about an event that contains just a single element from the universal set, we refer to that as an elementary event. But it's possible for an event to contain or to correspond to many different outcomes. So for example, an event could be rolling an even number on a six-sided dice. So we would say that even is an event, and it would contain the outcomes or elements 2, 4, and 6. And a trial is basically just the act of performing an experiment to generate a single event. So a trial would be rolling the six-sided dice a single time, flipping a coin a single time, taking a single reading from the output of a noisy sensor, something like that. So we get a random outcome, but we get only a single random outcome.